Junction field effect transistor is of two types. So N-channel Jfet and P-channel Jfet. These are the two types. N-channel Jfet and P-channel Jfet are the types of Jfet. And the terminals of FET, so either it may be Jfet or MOSFET, the terminal names are same: gate, source, and drain. Drain, source, gate. So these are the three terminals of the Jfet, and also the same names are given to MOSFET also. Okay. Now let us see the construction of N-channel Jfet. We have two types, N-channel Jfet and P-channel Jfet. So first one is N-channel Jfet. So in the N-channel Jfet, first N-type substrate will be taken. N-type substrate are will be taken, and for this wafer, on both sides, the P-type impurities are diffused. P-type heavily doped P-type impurities are diffused on both sides of this N-type semiconductor bar. And when you have two different materials, P and N regions, definitely there will be a depletion layer between P and N regions. So here we will be getting two depletion layers. So between P and N region, we have one depletion layer, and similarly between this P and this N region, we have one more depletion layer. And the region between these two depletion layers is called as N-channel. The region between these two depletion layers in the N-type semiconductor bar is called as the channel, and this is of N-type material. So we call this as N-channel. So N-type channel. Next, so these two P-type materials are combined together and called as a terminal, gate terminal. So this is gate terminal. Okay, two P regions are combined together with the help of metal contact, and this is called as a gate terminal. And one end of this semiconductor bar is called as a source, and the other end of the semiconductor bar is called as drain. So lower end is here in this case the source, and the upper end is called as the drain terminal. So total we have three terminals: gate terminal, source terminal, and a drain terminal. Now if you see the type of materials for these terminals, gate is of P-type material, source and drain are of same material, that is N-type. Gate is of P-type material, drain and source are of N-type material. And now let us see this symbol. So this is the symbol of the N-channel Jfet. N-channel Jfet. So gate, source, drain are the terminals, and there is arrow mark on the gate terminal. So arrow mark is there on gate terminal for Jfet and also for Jfet, N-channel and P-channel Jfet, arrow mark is there on gate terminal. So whereas if you take BJT, arrow mark is there on the emitter terminal, but here arrow mark is there on the gate terminal. And this arrow mark indicates the direction of current flow when gate source junction is forward bias. When gate source junction is forward bias, that means now see, gate is of P type and source is of N type. So whenever this is forward bias, current will be flowing from P type material to the N type material. So this is the direction of current flow. That means inverts the transistor. So that is why the arrow mark is inverts the transistor for N-channel Jfet. So this is the same thing, N-channel Jfet. Now let us see the P-channel Jfet. Now for P-channel Jfet, the substrate taken is of P-type. For N-channel, substrate is N-type. For P-channel, substrate is P-type. Substrate is P-type. And for both the sides, we have N-type diffusions. N-type heavily doped N-type diffusions are made and connected together called as gate terminal, and one end of the bar is called as source and the other end is called as the drain terminal, and the region between these two gate regions is called as a channel. And this construction is similar to the N-channel only, but opposite material for gate, source and the drain. So previously for N-channel, gate is of P-type, source, drain are of N-type. Now here gate is of N-type and source, drain are of P-type. So that is the only difference. And one more thing is, in the symbol, the arrow mark is indicating the direction of current flow whenever gate source junction is forward bias. Now you observe, whenever gate source junction is forward bias, and now gate is of N type and source is of P type. So whenever this is forward bias means current flows from P region to N region. So in this way current flows outwards the transistor. So therefore outwards the transistor. So this is the direction. Okay, so coming to the operation of N-channel Jfet. Okay, next. So in order to understand the working, we need to give proper biasing. So now as we have seen, so two junctions are there here. So here this biasing is given between gate and source. One biasing is given between gate and source. That biasing is VGG, that applied voltage is VGG between gate and source. And the other voltage is applied between drain and source. Other voltage is applied between drain and source. So this is VGG, which is applied between gate terminal, and this is source terminal, that is VGG. And another voltage, that is VDD, is applied between drain terminal and source terminal, drain terminal and source terminal. Now, so this voltage VGG is applied such that it will reverse bias the PN junction. It will reverse bias the gate source PN junction. Now, so the you will get generally one doubt, that is arrow mark is indicated. Arrow mark is indicated in the symbol. So which is making the gate source junction forward bias. So the arrow mark is indicated such that gate source junction is forward bias, but in the working of the Jfet, this gate source junction is reverse bias. Gate source junction is reverse bias. So this difference you have to understand. So in the symbol, arrow mark is indicated such that gate source junction is forward bias. But in general, in the working, gate source junction is reverse bias. The applied voltage is such that gate source junction is reverse bias. So please note this difference. Now, so that now this gate is of P-type material. So here negative terminal of the supply VCC is connected to gate, and positive terminal of this supply is connected to the source terminal. So that this gate source junction will be reverse biased. And next, let us see this VDD polarity. Now this VDD is applied such that it will make the charge carriers to flow from source to drain. It will make the charge carriers to flow from source to drain. Now, here in N-channel Jfet, the channel is of N type. So the channel consists of majority charge carriers as electrons, because this is of N type. So you have electrons here, electrons in this channel. So to move the electrons, the terminal, source terminal must be connected to the negative terminal of the supply, so that this negative terminal will pushes the electrons in the channel, so that they will move from source to drain region, and from drain region they will be collected by this positive terminal of the supply. So in this way you need to connect the polarity. For this VDD, you need to connect the terminals of VDD. So positive terminal is connected to drain and negative terminal is connected to the source. And coming to VGG, negative terminal is connected to gate and positive terminal is connected to the source, so that gate source junction is reverse biased. So why this is actually means, why we have to make this reverse bias means to control the width of the channel. So here gate source junction is reverse biased. And here you see this VDD you are applying so that you are moving the charge carriers to move the charge carriers from source to drain, So for that purpose, we'll connect the VDD. Next, coming to this VGG. So this VGG is connected so that the gate source junction is reverse bias. This is because to control the width of the channel. To control the width of the channel. To control the width of the channel will reverse bias this particular gate source junction. So what actually happens if we go on increase the applied voltage, this depletion layer width increases. This is because as reverse bias increases, we know that the width of the depletion layer increases. So as the width of this depletion layers increases, the width of the channel, conducting channel width will be decreased. So in this way, by applying this voltage between gate and source terminals, we can control the width of the channel in the Jfet. So this is the purpose of VGG, and purpose of VDD is to move the charge carrier so that current will flow through the transistor. Okay. Now, so in order to understand the working of this particular circuit, so let us see the first condition. So in the first condition, assume that the first condition, yes, as we have two supplies, generally we'll get four conditions. So when VGG is 0 and also VDD is 0, then what will happen? VGG is 0 means no reverse biasing is given, and also next VDD is 0, that means no charge carrier will move in the transistor, that means no current flow, no current flow in the transistor, that is ID is equal to 0, drain current will be 0. So this is the first condition. Next condition, when VGG is increased, when VGG is increased and VDD is 0. So when you give VDD, then only charge carriers will move. Okay. So no charge carrier movement will be there. So in this case also, drain current is 0. In this case also, drain current is 0. But what happens as VGG increased? Now you can see this VGG is applied between gate and source. Now if I indicate VGS, which is the voltage between gate and source terminals, so plus minus, that means as you increase the magnitude of VGG, VGS will go negative. So VGS will go negative. So when VGS go negative, then this PN junction will be reverse bias, or else in order to avoid confusion, simply now you can see P type is connected to negative terminal and source is connected to the positive terminal. So therefore it is reverse bias as you go on increase the magnitude here. Okay. Now in that case, what happens? This depletion layer width will be increased. Depletion layer width will be increased. So that is the effect of VGG on the depletion layer width. And no current flow is there because VDD is 0. Next, one more thing is, when you still go on increase this VGS, still go on increase this VGG, means VGS increased negatively, and at a certain voltage called as VGS off, at a certain voltage called as VGS off, if you go on increase this reverse bias voltage, depletion layer width will go on increase, depletion layer width will go on increase, and at a certain voltage, these two depletion regions will make contact with each other, will make contact with each other. In that case, we say that the channel is cut off. Channel is cut off. So in that condition, even though you apply VDD, no movement of charge carriers. Okay, when VDD is 0, ID is 0, and when VGG is increased negatively, then at a certain voltage, as the reverse bias voltage increases the depletion layer width, so at a certain voltage called as VGS off, two depletion regions will make contact with each other, making the channel width 0. That means we say that channel is completely cut off. Okay, so this is the second condition. Next, third condition. Now in the third condition, VGG is 0. Third condition, VGG is 0. And now VDS is increased from 0. Now VDS is increased from 0. So VGG 0 means simply gate source voltage is 0 means simply they are shorted. Next, now we are going to increase this VDD. Now as the magnitude of VDD increases, then what happens? So this will pushes the electrons. The negative terminal will pushes the electrons in this N channel from source to drain, and these electrons will be collected by this positive terminal. So in this way, electrons are moving from source to drain, and the conventional current direction is opposite to the electron flow. Therefore, drain current direction is from this drain to source. So this is the direction of ID. So electrons are moving in this direction, and conventional current direction is opposite. So this is the direction of ID. Now, so for smaller magnitudes, if you go on increase the applied voltage, current through the PN junction, current through this channel, N channel also increases. Current through the N channel also increases. So now as current through this channel increases, the curve will be like this. If you plot the graph between the applied voltage for this, between the drain and source VDS and drain current ID. Now initially for smaller voltages, if you go on increase the voltage, current also increases. Now, so but what actually happens is at a particular voltage called as pinch of voltage. Now see, as the current increases in the channel, so there will be resistance in the channel. So every material has some internal resistance. Similarly, this drain is also have. Yes, so let me draw here once. So this region, so channel region is also having some internal resistance. Say for example, so this internal resistance is divided into 4 parts. So that means the channel is uniform in doping and all. So therefore, the uniform resistance will be there in the channel. So let us assume this is all are equal. Okay, because it is uniformly doped. So resistance is also uniformly distributed throughout the channel. Now, let us assume that this VDD is equal to 4 volts. Applied voltage is equal to 4 volts. That means here at this point, so plus 4 means here drain terminal. So here at the drain you are applying plus 4. Here plus 4 and here source is 0. Is at 0. So between drain and source it is 4 volts. Now, so by applying potential divider rule, now what will happen? This 4 volts will be dropped across these resistors equally. So that means here 1 volt will be dropped, here 1 volt will be dropped, here 1 and here 1. Okay. Now, but now if you observe here, what is the voltage at this point? 4 minus 1. So 4 minus 1, that is 3 volts will be there. And similarly here, 4 minus 1 minus 1. So that is 2 volts. And similarly at this point, the voltage is 1 volt. Now this is the voltage in the N channel. So that is in the N region. In the N region, these are the different voltages that you observe throughout the channel. So the complete voltage VDD is distributed into this channel. Now, as VGG is 0, now gate terminal is at 0 potential. And so in the channel, you have different voltages. Say here you have 3 volts, here drain is at 4 and source is at 0. Now in between here we have 3 volts, 2 volts and 1 volt like this. Now in this case what happens? Now you observe here P type is connected to 0 potential and this N region is having 3 volts here. Means it is having 3 means plus 3, right? Here this is a positive voltage. Plus 3 plus. Okay. Now P type is at 0 potential and N type is at plus 3. That means it is reverse bias. And this voltage is more. So therefore, as the reverse bias voltage is more width of the depletion region is also more. So here the width of the depletion region is more. Here at a plus 3 volts. Similarly, now you have plus 2 volts. This is somewhat lesser voltage compared to this one, lesser reverse bias voltage. So the depletion layer width is also lesser compared to the this place. And similarly, if you go down, then the reverse bias voltage decreases. So therefore, the width of the depletion layer also decreases. So in this way, the width of the depletion layer is more near the drain terminal and it is less near the source terminal. So this is due to the internal resistance property of the Jfet. Okay, now what is happening at a particular voltage? So these reverse bias voltage will make these two depletion layers increases. Now you can see in this second diagram, now you can see, yes, let me rub this portion so that it will be more clear for you. So in the first case, say the applied voltage is less compared to the previous case. Say here the applied voltage is 2 volts. Applied voltage is 2 volts. So therefore the width of the depletion layer is less here. And one more thing here, this width is more near to drain and less near to the source. And if you still go on increase the applied voltage here, now in this case it is 4 volts. Now what happens? So more reverse biasing will be there near the drain. So therefore depletion layer width will be more compared to the previous case. Here lesser voltage, lesser depletion layer. So that width of the channel is more here. And now here for higher voltage, the width of the depletion layer is more and the width of the channel is less here. Now you observe this difference. We require this channel width. Okay. So through this channel only charge carriers will move. Now this width decreases. So this width decreases. That means there is no further increment in the current flow. There is no further increment in the current flow. In that case, we say that channel is pinched off. Channel is pinched off. At a particular initially when VDS increases, ID current increases, and but at a certain voltage called as VDS is equal to VP, the current ID will not go beyond a certain current called as IDSS. IDSS. So here at a particular voltage called as VP, we say that channel is pinched off. Channel is pinched off, and there is no further increment in this current because channel length is minimum. Channel width is minimum here. Channel width is minimum. So that current cannot go beyond this value. And this value of current is called as IDSS, drain to source current with gate shorted. So drain to source current, drain to source current with gate voltage 0 or VGG 0 or gate shorted, we can say. Yes, this diagram shows when VDS is equal to VP, that is when under pinch off condition. So when VDD is equal to VP means making VDS is equal to VP. Okay, this voltage appears across a drain to source. That is why we call this as VDS voltage, drain to source voltage. Both are same. VDS and VDD are same in this case. Okay, so at pinch off, we have maximum current that is flowing through the circuit, that is IDSS. IDSS. Okay, now the same characteristics now you see here. On x-axis, we have VDS, drain to source voltage. On x-axis, we have drain current ID. So initially, as VDS increases, current increases ID, and at a certain voltage called as VP, channel is pinched off and constant current flows through the channel. That current is IDSS. And if you still go on increase this VDS at a particular voltage called as breakdown voltage due to avalanche breakdown in this depletion layers. So always we know that this avalanche breakdown occurs due to the increment in the charge carriers, carrier multiplication, which occurs in the depletion layer. Okay, at a certain voltage. So therefore, due to that, what happens? More charge carriers will be generated in this region, and they will be moving in the properly connected circuit, which is leading to higher current, large amount of current flows, which will break down the transistor. So this region must be avoided for Jfet. Okay, these are the characteristics under VGS is equal to 0. So that is the third condition. So when VGG is 0, VDS is increased, we have seen the operation of the circuit. And now we will see the fourth condition. So under fourth condition, now VGG is increased, means VGS is negative. So VGS is negative voltage, and also VDS is increased. So VDD increased. So VDD increased means VDS is positive. You know that. So anyhow, no need to mention. Here VGS is negative, so that's why we need to mention. Okay, so this is the condition. In the second diagram, you can see that. So now we are applying VGG and also we are applying VDD. So both the voltages are applied. Now compared to the previous case, when VGG is equal to 0, now the width of the depletion layers is more because you are going to apply some negative voltage. See, VGG is 1 means VGS here will be plus minus. So this magnitude will be minus 1 volt if you measure between these two. Okay. So in that way, this p type is connected to negative terminal and n type is at some say zero potential. In that case, the width of the depletion layer increases. And now you go on increase this VDD, then current increases. But this current, the magnitude of this current is very less compared to the previous case because the width of the depletion layer increases, the width of the channel decreases. Okay, so less number of charge carriers moves leading to less current compared to the previous case. That is when VGG is equal to 0. So as you go on increase this VGG, then what is happening? The width of the depletion layer increases, which decreases the width of the channel. So the magnitude of the drain current decreases. In this way, this VGG is, that is the voltage applied between gate and source. VGS is controlling the drain current. So that is why we call this Jfet as voltage controlled device. Voltage controlled device. The voltage applied between gate and source is controlling the width, which eventually controls the magnitude of the current. So that is why it is voltage controlled device. Now you can see the complete characteristics of N-channel Jfet in this case. So the first curve is similar. We have already discussed when VGS is equal to 0, initially current increases and it remains constant after VT, pinch off voltage, and thereafter it increases at a breakdown voltage. So this is that curve. Next, when VGS is equal to, that means when VGG increased. When VGG increased, that means VGS is going negative. VGS is going negative, so that means VGS is minus 1 volt. In that case, width of the channel decreases compared to the previous case. The current also decreases. Current also less compared to the previous case. And if you still go on increase VGG and VGS is going negative, so the current is still decreases. In this way, if you go on increase VGG, that is VGS negatively, you go on increase, the current, drain current decreases. Drain current decreases. And the transfer characteristics. So transfer characteristics, these are the drain characteristics or output characteristics drawn between output voltage VDS and ID for Jfet. And the transfer characteristics are drawn between input voltage that is VGS and output current that is drain current. So this is output current and output voltage, whereas here this is input voltage on x-axis and output current on y-axis. So these are transfer characteristics, these are drain characteristics. So from drain characteristics only we can obtain these transfer characteristics. Once, if you look at when VGS, so this is VGS is equal to 0. When VGS is equal to 0 at the pinch off voltage, I am plotting the curve, transfer characteristic curve. Or else at VDS is equal to constant. At constant VDS, we'll draw the curve. Okay, we have drawn this one in the lab also. Okay. So initially we put the VDS is equal to 1 volt, we got one curve. Again, when we put VDS is equal to 3 volts, we got one more curve this way. So when at a particular constant voltage, say here I am taking at VP. Now VGS is equal to 0. So when VGS is equal to 0, what is the current? Drain current IDSS. So when VGS is 0, drain current is IDSS, maximum value. And similarly, when VGS is equal to minus 1 volt, now what is the current? It is lesser compared to previous case. Say here it is minus 1 volt. Okay. So here it is lesser compared to the previous case. Similarly, when VGS is equal to 2 volts, here minus 2 volts, current further decreases. And VGS is equal to minus 3, say minus 3, current further decreases. And at a particular voltage called as pinch off voltage, this current completely becomes 0. VGS is equal to VT. Then this current completely, drain current completely becomes 0. So in this way, we can plot the transfer characteristics. And if you look at the drain characteristics, we have 3 regions of operation. So similar to the BJT is having active region, cutoff region, and saturation region. So Jfet is also having 3 regions of operation. So first one is the ohmic region. So This is also called as linear region. So linear region. And second one is active region. So active region, or it is also called as saturation region, because current is constant in this region. And then third region is breakdown region. Breakdown region. So this region must be avoided. And one more is there, that is cutoff region. So generally we don't mention this breakdown region. So this is treated as the other region, that is cutoff region. Ohmic region, active region, or saturation region, cutoff region. So cutoff region is not shown here. This is the cutoff region, so which is near to x-axis. So in which drain current is almost zero. So cutoff region. So here this acts as Jfet acts as off switch. So because current is zero, as the current is zero, it acts as open switch or off switch. And in the saturation region, the current is almost constant. So it acts as on switch. So in these two regions, the Jfet is used as a switch. Jfet is used as a switch. In active region or saturation region and cutoff region, Jfet acts as a switch. And in the ohmic region or linear region, Jfet acts as the amplifier. Jfet acts as the amplifier. So applications are same as the BJT. Okay, so transfer characteristics are defined by one equation called as the Shockley's equation. So this equation gives the relation between drain current ID and gate to source voltage VGS. So it gives a relation between drain current and gate to source voltage ID and VGS. Okay, so ID and VGS. So which is equal to ID is equal to IDSS into 1 minus VGS by VGS of whole square. Now from this equation also we can plot the characteristic curve. Okay, that is VGS, and here this is the ID. When you put VGS is equal to 0 in this equation, the second term will become 0, so that ID is equal to IDSS into this 1. So this total thing will be 0. So simply it is IDSS. IDSS. And when you put VGS is equal to VGS of, these two are equal. So VGS of by VGS of, that is 1. So 1 minus 1, it is 0. So 0 into something is 0. So here at VGS is equal to VGS of, the drain current is 0. So in this way also you can plot the curve. Now, so if you understand this N-channel Jfet, this P-channel Jfet is similar. Here the type substrate type taken is P-type material, and two N-type impurities are diffused on both sides. This thing we discussed, and they combinedly called as gate terminal. And one end is called as source and the other end is called as the drain. Now coming to the supplies here, VGG and VDD. So there for N channel, VGG negative terminal is connected. Here positive terminal of VGG is connected to N-type material, so that it makes gate source junction reverse bias. N-type is connected to positive terminal, P-type source is connected to negative terminal, making gate source junction reverse bias. And now coming to this VDD. So here VDD negative terminal is connected to drain, and positive terminal is connected to source. So which is opposite to the case of N channel Jfet. In P channel Jfet, we have holes as the majority carriers. In order to move these holes from source to drain, we need to connect the positive terminal of the supply. So this positive terminal pushes the holes in this source to the drain. So from source towards the drain, they will travel and they will be collected at the negative terminal, we can say. And in this case, the direction of current is same as the hole flow, because holes are moving from source to drain. The conventional current direction is same as the hole flow. Therefore, this is the drain current. So drain current direction is from source to drain. So this is the direction of drain current. So this is the difference between N channel and P channel. And coming to the characteristics, so characteristics are completely opposite. So there VDS is positive, here VDS is negative. and drain current direction is also opposite. And coming to this VGG, there VGG increases means VGS is going negative, but here when VGC increases, so VGS becomes a positive. So becomes positive. So initially when it is zero, maximum current flows, and if you go on increasing positive voltage at the gate source junction, it will increase the depletion layer width. So therefore, as you go on increase VGS, current decreases. Same as the N-channel Jfet, only the thing is there VGS was negative, here VGS is positive. So that is the only difference. And if you look at the transfer characteristics also, VGS there it was negative, now here this VGS is positive. So simply you can flip or else this is like a mirror image of characteristics of N-channel Jfet.